Hey,
Hi, can you hear me?
I can hear you. Can you hear me?
Can you hear me?
I can hear you.
Hi,
Yes.
Nils, can you hear me?
Yes, I do. Give
Can
me
we
a
try
second.
that
Can
again,
you hear me
please,
now?
Nils?
Yeah, can you hear me now? I can hear you.
Can you try and speak to me? Can you hear me?
Can you hear me?
Can you say hello, Nils?
Hello, I can hear you.
Cool. You're all good to go.
I'm good to go. Perfect. So, yeah, hello. Thank you for the opportunity to present today. My name is Nils Hutter. I'm a postdoc at the University of Washington, working together with Cecilia Bitz. But today I want to present you some work that I've still done as part of my PhD at the Alfred Wegener Institute. And before I jump into the talk, I want to take the opportunity to acknowledge all my co-authors. And first and foremost, Amélie Bouchard, who from McGill University, who co-led this project together with me and performed a major part of the analysis that I'm going to show today. So today I want to talk about the Sea Ice Rheology Experiment, short SIREx, which is a model intercomparison project in which we compared simulated and observed deformation fields with the goal to better understand how different rheologies reproduce deformation and what those differences in those rheologies are. And in addition to that, that was also a good opportunity or a point in time to basically evaluate where we are at with representing small-scale deformation. So let's jump into what basically the motivation for this project was. So we started it back in 2017, and at the time, more and more simulations were presented by different groups that basically showed that they could resolve linear kinematic features. So linear kinematic features are zones of localized deformation where basically you have leads of pressure.
Yes, sorry, it's Pierre speaking now. On the chat, it seems like they don't hear you over there in Cambridge. So if you could please wait for them to sort out the technical issues. I'm just reading the chat right now, and Jake is saying, please wait.
Oh, thank you so much, Pierre. But you can hear me?
Yes, we can all hear you, but apparently they can't.
Okay.
It was really nice, by the way. Nice start.
Yeah, thank you. I will try to give it again. Go.
One, two, one, one, two. The issue that I've got. 1, 2, 2. One, two, two, two. Hi, Nils. Can you try saying hello and counting to 5 for me, please?
Hello. 1, 2, 3, 4, 5. Can you hear me now? If you want, I can continue saying something.
All right.
One, two. Hi, Nils. Can you just count to 5 for me so I can see if I can hear anything?
Yeah. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2. 3, 4.
I'm having real issues with getting sound from you to my sound.
But can you hear me? Or
I
is
can
it
hear
just
you in the box, but I can't hear you out of my front of house, which is proper strange.
Huh.
Can you say hello for me?
Hello. Yeah, I can continue speaking. Hello. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
Another audio. Oops.
Hey, Bruno. Does it work now? Let's see. That's for sure a funny morning exercise, I need to say. Please let me know if I should continue saying something for the... Okay. That's funny. Oh, it's nice. Now I can see the people in the room.
Can you now hear me, Nils?
I can hear you, yeah. Can you hear me?
Okay, so I'm going with something. So yes.
Okay. So are we ready to start again?
You can. Yeah, I'll sort that now.
Okay, so then I'll give it a start. Just interrupt me whenever there's another issue, please. Okay, so hello again. Yeah, thank you for that it now works that I can speak. So my name, for all of you who don't know me, my name is Nils Hutter. I'm a postdoc at the University of Washington and working with Cecilia Bitz. But today I want to present you some work that I started as a graduate student at the Alfred Wegener Institute back in Germany. Before I start this presentation, I would like to take a moment and acknowledge my co-authors, and first and most importantly, Amélie Bouchard from McGill University, who co-led this project with me and performed a major part of the analysis that I'm going to show today. So the talk today is about the Sea Ice Rheology Experiment, or short SIREx, which is a model intercomparison project which compared simulated and observed deformation fields with the goal to better understand how different rheologies represent this deformation. And how those. So the motivation for this work, when we started it, I think back in 2017, was that there were several groups who started to present simulations that actually could directly resolve deformation, like leads and pressure ridges, so zones of localized deformations, which are often referred to as LKFs. And back then it was not sure what there was a huge discussion what is necessary to resolve those. So different rheologies were suggested, high resolution applications were suggested. And with this project, we wanted to address this question of basically what different kinds of ingredients are needed for representing deformation right in our simulations. And that is basically directly led us to the next question: how can we judge whether our model reproduces deformation correctly or in a good way compared to observations? And that was then, what kind of metrics can we actually use to evaluate those systems? There were a few different approaches out there back then. And the idea was basically to compare which of those actually can distinguish between rheologies or different other parameters that impact the quality of deformation fields. So how did we design this intercomparison project? So basically what we did is we started with a very low entry level requirement, with the idea to have more groups joining the effort. And the idea was we wanted to compare sea ice deformations of 2 winters, namely January, February, March of 1997 and 2008, with RGPS, which is a satellite sea ice drift and deformation data set that is done by tracking ice in SAR images. And what models needed to do to participate is basically submit for those 3 months, for at least 1 year, daily ice velocities, concentration, and thickness fields. And in the end, we ended up by 10 different groups participating in this intercomparison, submitting simulations from 11 different models. And you can see on the right, I try to summarize the diversity of those simulations. So, like, first importantly, from the name Sea Ice Rheology Experiment, we have simulations of 3 different kinds of rheologies. One is the most commonly used VP-EVP rheology, but we also have the anisotropic EAP rheology, and we also have simulations with the Maxwell elastobrittle rheology. But this, in addition to the rheology, also the simulation differ, for example, in the spatial resolution that they use, ranging from something like 15 kilometers down to 1 kilometer. They differ in what kind of atmospheric forcing they use, what kind of resolution this has, or, for example, the number of ITD classes, going from the standard Hibbler 2 ice classes to something like 10. And also not shown here in the plots is that also, for example, the ice strength parameterization for some of those models is different, and the accuracy in the numeric solution is also different for some of the simulations. So to analyze those whole set of simulations, in total 38 simulations, we split the analysis in 2 main parts. And the first part addresses more the traditional scaling metrics that have been used so far, that you also saw in the talk from Antoine. And the second part is doing spatial and temporal statistics on LKFs. And I want to go a bit, give you some more insights what this is about. So the first part of SIREx is about scaling metrics. There we take a look. That is work that Amelie did and is published in her SIREx paper. And basically what we're doing there is we're taking the deformation field, and then we want to ask different questions on the deformation physics. So first we can look into the PDF of deformation rates and basically check how large deformation rates can get. Can we reproduce this really high deformation rates that we observe in LKFs? The second part would be we can do a spatial and temporal scaling analysis, so computing deformation at different spatial and temporal scales, see if we find a power law scaling and then get a sense how localized deformation is in space and time. And the last most complicated statistic in this series is then the multi-fractal analysis, where we can basically again compute deformation rates at different spatial and temporal scales and also at different moments, and test then basically how this localization of deformation changes with the deformation intensity, and see if we find multi-fractal deformation. And the second part is the work that I've done, which is LKF statistics. It's a slightly different approach, more from a user perspective that is interested in where those leads are, how long they stay open, and so on. So what we're doing there is we're taking, again, our deformation fields, and then we apply an automated detection and tracking algorithm for pressure, like for LKFs. I try to denote them here in the plot with those black lines. So this is basically what the algorithm picks as lead or pressure ridge. And from those, we can then derive different spatial properties, for example, like LKF densities. So where do LKFs form? Where are regions where we have a lot of LKFs? We can look at what sizes they actually have, how long they are. But we can also look, for example, if two LKFs are intersecting, at what angles do they do? Because that holds some information about the underlying rheology properties. But we can also do temporal property statistics. So we can, for example, look into how long does a lead stay open and look at the lifetime of LKFs, or look at how fast they're growing. And since actually the results that we have filling like 2 overlength paper, I won't have time to go like in all of the different details. So I basically try to mix a bit results from both parts together to come up with some main conclusions. But whenever you have later on questions to individual statistics, I'm also happy to answer them. So I suggest we start with a rather simplistic statistic to get easy into, and this is the probability density or distribution functions of deformation rates, where we basically just compute the PDF for here now, in this case, shear rate. And on the top panel, you can see the models grouped by the resolution. So those are roughly models with a resolution of 10 kilometers. And the lower panel, you have high resolution simulations, which are going down from 4 to 2 kilometers. And previously, mostly what people were looking at is at the slope of the tail of this PDF, assuming that it's a power law scaling, and then basically compared the numbers of the slope. However, if we take a closer look, we will find that there are PDFs that actually have the same slope, but actually are quite like distinct from each other and are not really a good representation. So one of the conclusions from Amelie was that actually the slope of the PDF alone is not really a useful metric. And instead, we then introduced another metric that we use in both parts of SIREx, which basically is used to compare heavy-tailed probability density functions. And what we're doing is we're computing the difference of the two, we're integrating the difference between the two PDFs, but in a logarithmic spacing. And thereby we're giving some extra weight on the tail that we otherwise might not like lose some information on. And then in addition to also reconsider that maybe if we are not reproducing very large deformation rates, there is also a misfit. We subdivide this integrated sum by the number of bins that actually the model is able to resolve deformation in. And if we do this, we get to this nice colorful plots. So basically for each row now you see a model and the difference to the RGPS PDF. Again, on the top panels, you see low resolution models, and in the lower panels, you see high resolution models. And here you see similar pictures as for this individual or for the PDFs itself, is that low resolution models seem to underrepresent the high deformation rates, so having a shorter tail. Whereas more of the high resolution models are in closer agreement with the RGPS, and actually here now marked in yellow, this is this cost metric or skill metric that we came up with, are all the models that are able to represent the PDF within the interannual variability of the RGPS. And you can see that from the low resolution models, mostly NextSim, which uses this Maxwell elastobrittle rheology, seems to be able to reproduce the RGPS despite the high resolution, and something that otherwise the VP models mainly manage to do at a high configuration setup, which points to that it seems like MEB can be run at coarser resolutions to obtain similar results as high resolution VP models. The other thing that I want to point out is that there is some models that have strong deviations, which I circled here in blue. And those are basically model simulations that were run with a lower solver accuracy. And meaning by that is that they use the EVP rheology and use the lower number of subcycles. And actually this degrades the deformation fields that you can simulate. And then I want to link this also to the second part of SIREx, like the detected LKFs that we find. And actually what we can find is that the models that perform well in the probability density functions of deformation rates actually also show a higher number of resolved LKFs. So that you can see here on the right-hand side plot where we plot the number of detected LKFs over the resolution. And basically those models that are marked here in yellow are the models that are up in this group. And for example, NextSim is the green dot here, which also shows the higher numbers of LKFs compared to the lower resolution, the other lower resolution simulations that we have. And that's a nice result because the deformation rate PDFs are a much easier to compute metric than detecting LKFs. And if we can use it as a proxy, that's a good sign. For example, if we want to use a simple metric for model tuning, for example. Going ahead from the number of LKFs, let's look. Number of LKFs basically means how many we resolved, and we can also take a look at where we resolve those. And that would be then the density of LKFs. And here, those are now a number of panels for each of the different simulation participating. In the uppermost left corner, you see the satellite observations from RGPS. And you can see actually that in observations, we find that LKFs are quite homogeneously distributed over the Arctic Ocean. There are slightly higher values in coastal regions, and there are also slightly higher values in the Beaufort Sea, but overall, it's a quite homogeneous distribution. If we look into most of the model simulations, we find a quite different picture. There we find that at the coastlines, the models seem to do an okay job by representing LKFs, but whenever in the pack ice, most models underestimate the density of LKFs quite strongly. And actually only models that are within the RGPS interannual variability in our comparison that reproduce pack ice LKFs reasonably well are models that have the ability to strongly locally reduce the ice strength in pack ice. And one way to do this in the MEB rheology is the damage parameter that we have in there. And the other simulation that is able to do so is the MIT GCM 2 Paloma ITD simulation that basically is able to, by the combination of the ITD and the Rothrock ice strengths, to have strong gradients in the ice strength. And one other thing that I want to point out here is now focusing on two pairs of simulations, which use different ice strength parameterizations. I enlarged this for you to maybe better see. So this is something, we had a couple of simulations that were basically run with the standard ellipse ratio of 2. And we had a few simulations where actually this ellipse ratio was reduced alongside with reducing also the P. And by reducing the ellipse ratio, we found that at least in the low resolution case, like here for the McGill model in the lower panel, you can see that actually we are able to increase the LKF densities also within pack ice. It's not as obvious in the high resolution case, but we were wondering if actually this, like more LKFs in pack ice, are pointing towards that we have higher localization in the deformation fields. And that is something that we can closer investigate by looking into the spatial scaling of the fields that was done in the first part of SIREx. And I just want to show you those results as well. So those is in the upper row, you can see again the McGill, the low resolution models, and the two right panels basically show you the deformation fields for the standard ellipse ratio of 2 and the reduced ellipse ratio of 0.7. In the lower panel, you see the MIT GCM simulations at 2 kilometer, again in the middle panel with ellipse ratio of 2, and on the right-hand side, the reduced ellipse ratio. And now on the left two panels, you see the spatial scaling analysis. Spatial scaling analysis is, as Antoine also showed earlier, is basically you compute the deformation rates at different spatial scales, and then look if the mean deformation rate at this spatial scale follows a power law scaling. So we're looking here if basically we find a linear line in our double logarithmic plot. And what you can see in this for this spatial scaling is that basically when we look at the standard ellipse ratio of 2, we find that there is a difference in the slope. But if we're reducing this ellipse ratio to lower values, actually we find a steepening in the spatial scaling, meaning that we have more localized deformation fields and thereby representing this characteristic of sea ice deformation. So now we've seen like one way how we can impact our results. Now we might be wondering what other parameters except for the ice strength may play a role in how well LKFs are simulated. And I want to go show you some results. This is from the second part of SIREx, where we take a look into what different parameters actually influences the simulated LKFs. And to do so, we computed skill metrics for all the different statistics that I named in the beginning. So LKF density, the intersection angle, LKF length, lifetime, and growth rate. They're color-coded, as you can see in the legend. And then we basically look how group the models into different groups depending on their from the spatial resolution in the upper left, the temporal resolution, forcing resolutions, rheology, and stuff like this. And what we find is that actually on the first side, we can say that there are also other configuration parameters that are equally important as the choice of rheology, as they also have a similar impact. And the ones that I want to name first is like starting on the left-hand side, like spatial resolution seems to matter. So especially for the LKF density, we find a much better agreement if we are reducing the resolution of our simulations. We also found that the temporal resolution at which the models are run, so the time step, has a huge impact on the density, but also on the length and the growth rates of the LKFs. And also, we could show that the spatial resolution of the atmospheric forcing fields that we are using also significantly improves the simulations. So those basically, in addition to the ice strength that I showed before, and also the accurate numerical solutions, are basically all things that you can use to improve your simulated LKFs fields that you have. But if you take a closely look at those plots here, you will also find that there are two metrics who are basically somehow independent of the other parameter choices that we take and don't show any big correlation to any of those parameter choices. And this is the intersection angle and the LKF lifetimes, which don't seem to be clearly correlated to any of those quantities here. And they're also, also in the first part, there are statistics that don't show like a big spread within the different models. And we have some statistics that basically all agree with RGPS. For example, the temporal and multi-fractal scaling that I want to come to in a minute. And we have others that don't agree at all with RGPS for all models. And this would be, for example, the intersection angles. So I want to spend the next 2 slides talking a bit about those metrics and what we can learn from those. So first, I want to start with the temporal and multi-fractal scaling. So this is again from the first part, where actually now on the 2 left plots, you can see the temporal scaling for all models compared to RGPS. And again, temporal scaling, we compute deformation at different temporal scales and look again for power law scaling of the mean deformation rates at different temporal scales. And what we actually found, or Amelie found, is that all models basically show a strong localization in time of sea ice deformation. So we all have this power law scaling, and all with a rather similar slope. So that's the first thing, that they all seem to represent that correctly. And the other statistics where we are surprised to see that all models reproduce this is the multi-fractal scaling. So when you do the scaling analysis also for different orders, moments than just the mean, and to look basically again how this localization changed with the intensity of the deformation. And also there, Amelie found that basically all models are able to reproduce multi-fractality in space and time. And before, those quantities were often linked to specific characteristics of the rheology that basically would be required to reproduce those. But the agreement with all the models in those statistics might point to that there are other sources, whether it's forcing or internal to sea ice, that might lead to the emergence of those statistics. The next statistic I want to talk about is the one that none of the models was able to reproduce, and this is LKF intersection angles. So on the top left, on the top panel, you see basically the PDF of the intersection angle, and below in this color plot, you see again the difference in the PDFs. And what we can see for the observations, that's the black line up here, the RGPS, is that we have a distinct peak at 40 to 50 degrees for an intersection angles, whereas most models actually have a peak around 90 degrees. And you can also see this in this big red part here in the middle. And actually no model is able to reproduce this peak at 45 degrees. However, there are a few simulations who are actually able to show, or which show lower skill metrics. I circled them here in gray, and you can see those are all the ones that basically use reduced ice strength, use reduced ellipse ratios and vary the ice strength of the ice. And that might give us some insight that actually with the different rheology choices, we are able to modify this, and that we actually could use this metric to learn more about what is the appropriate rheology or appropriate yield curves to use, and how we can constrain this better. And this is ongoing work by Damien that I think also presented earlier today, and might be excited to have a closer look to. And with this, I want to end this talk with the conclusions. We have a very large set of conclusions, so I slowly go through them. So I want to start with some scientific insights that we got from SIREx. And I think the first and most important one is that actually we could show that different model configuration parameters, like for example, the spatial resolution or the atmospheric forcing that we use, and also physical parameterizations as the ice strength or the ITD, actually have an impact as important as the choice of sea ice rheology for the deformation statistics that we use. However, we could find that the Lagrangian MEV simulation from Nextsim that was in our comparison seemed to show stronger localization and more realistic LKFs at a coarser resolution than E or EVP models at a similar resolution. And we also could point out to maybe some new statistics that could be used to improve the rheology that seem to be linked, as for example, the LKF intersection angles that are linked to the rheology, and no model so far is able to reproduce those. We also have, especially Amelie has a strong section in her paper about what we can learn from SIREx for the interpretation of the existing metrics of sea ice deformation. And for example, like as shortly talked about, the multi-fractal characteristics and the temporal scaling are basically apparent in all simulation, despite the choice of rheology, and might be therefore, interesting to dig a bit deeper into and learning how or what actually is the reason for that. Also, we found that the spatial scaling of deformation rates and the deformation rate PDFs are linked to the LKF density and numbers, but actually we didn't find any other link between scaling characteristics and temporal and spatial and temporal LKFs, especially not from temporal scaling, for example, to temporal characteristics of LKFs like lifetime. So that means basically you can use PDFs and scaling to get some information about the density and numbers, but other important properties like, for example, how long does the lead stay open to basically get an idea how much heat exchange happened there cannot be deduced from those scaling statistics. And I want to end on some hands-on advice for configuration design and tuning. So what you could do basically to improve your model if you're interested. And starting first with the PDS of deformation rates seem to be a very easy to compute metric and seem to be a good proxy for some other more complicated statistic pointing to better spatial scaling, but maybe also to better LKF densities and numbers. So that might be something that you want to use if you do systematic model tuning, for example. We could also show that in EVP or VP models, the solver accuracy and also the eye strength parameter have a strong impact. So whenever you design a configuration or simulation, take some moments to closely think about those. And if you're interested in having more sophisticated statistics within your tuning or in-depth analysis, we also developed quantitative metrics for all the other statistics there. So, and we are happy to share them. And if you want to learn more about those, the two papers of this intercomparison project were both published in JGR Oceans in, I think, May this year. So if you want to have a closer look. And also one other note, all the data that we used, so all the model data and also the observational data are published on Zenodo. So whenever you want to have a look at those fields on your own, you can go there and just download them. And with this, I want to finish. And in case there are questions, I'm happy to take them.
I don't know if you can hear me, Nils, and see me, hopefully. But thank you for that. I didn't get a chance to introduce you, but that was Nils Hutter from University of Washington. I know we're overrunning slightly, but I'd like to take a couple of questions if there are any.
Hi, Nils. I don't know if you can hear me. If you can, make yourself known some way.
I can hear you.
Fantastic. Okay. Are you in Washington? I thought you were in RV. Okay. My mistake.
I'm in Washington.
Okay. Lovely talk, first off. I guess I wanted to make one comment, and it's slightly random, and it's not meant to be critical in any way, but it's just a note, something to note. You pointed out a couple of times that changing the aspect ratio of the yield curve had quite significant impact on various metrics of the deformation and the LKFs, which was interesting. Okay. I think a lot of people would probably feel it's a little unphysical to systematically alter the elliptic yield curve ratio in such a way. Okay. I'm not saying I would, I'm saying some people would. Okay. What I would add to that, though, is that one of the rheologies you looked at was the elastic anisotropic plastic rheology. Okay, and what you may not fully realize is that doesn't actually have a yield curve. Okay, but it effectively has a yield curve, which does give fatter yield curves than the others, and it does that because of the anisotropy in the model. And so I would argue this is a relatively physical, dare I say, even realistic way of getting these fat yield curves, which do actually seem to improve your deformation characteristics. And that's at least one slightly more physical route into doing that than just saying, hey, let's turn the yield curve on its end.
Yeah, thank you, Danny. That's a good comment. I mean, one of we had the EAP, the anisotropic rheology, in our comparison, but actually it was only just one simulation. So it would be very interesting to look into this and to closer with more simulation with that rheology as well. Yeah, thank you for making this clear.
Okay, we have time for one more question. Okay, one more question. Going, is that handy? No? Okay, well, I think we'll end it there then, and we'll thank all our speakers again.